Oh, do you want me to not record that? Maybe we shouldn't. I
I
usually
don't
don't, but then like people could be, I don't know if people feel more open if they're not
care.
recording now.
Yeah, okay. Okay. So this is something we've been talking about doing for a while is contaminant transport from indoors to outdoors. And so what I'm going to focus on mostly is particles. I'm going to have a little bit about gases, and the part about gases is actually out from outside of the living space, not totally outside of the whole home. It's also going to be a lot of literature review. So it's not actually mostly my own work, except for the slides that are on gases. It's more, what is there in the literature that I think might be of interest to people to be thinking about how all of this stuff works. And so focusing mostly on particles, there are really two metrics that I see in the literature. One is called penetration factor, and that's the one I'm going to be talking about the most, but I'm going to talk a little bit also about the indoor-outdoor ratio. Penetration factor is just how much of what's outside gets inside. It depends on how much airflow there is from inside or from outside to inside. And it depends on the dimensions of the cracks that the air is going through, and it depends on the driving forces. The indoor-outdoor ratio, well, part of it is the outdoor, so it still depends on the penetration factor, but it also depends on what's generated indoors and other loss mechanisms, which I'll talk about in a little bit. And just at really fundamental level, in order for stuff to go from outdoors to indoors, you need two things. You've got to have a hole, and that's the crack. You've got to have a pressure difference, which can come from stack or wind or fans. So the stack and wind, that's a lot of what Tammy and Dom have been working on. But you can have a huge pressure difference. If there's no holes, you're not getting anything going from outside to inside. And you can have huge holes. If you don't have a pressure difference, you're not having anything go from outside to inside. So you really have to have both of these. And particles are going to move with air, but again, with some loss mechanisms. Particles being not just gases, have these additional ways that they get removed from air. So this is a schematic from Thatcher et al. From way back in 2003. It's not my favorite, but it's got the basic idea. You got a lot of stuff outside, some of it's coming in, you've got stuff inside that's going out, and there's other mechanisms like deposition that where particles can fall out or diffuse out of the air. So they get removed from just floating around the air. One thing this doesn't really show is as air with particles in it is going through thin cracks. If we're talking about building elements like insulated walls, the insulation acts as a bit of a filter. And so one of the removal mechanisms going from outdoors to indoors is removal through the building materials themselves. So, which doesn't necessarily catch gases. What it means then is that the amount of outdoor air coming in is likely going to be more than the particle transport. This graph I wanted to show just because I think it points out how important particle size is. On the left, this is about penetration factor on the left. And so we've got particle diameter on the bottom. So from really tiny particles up to 10 micron particles, this is the penetration factor for these different size particles. And you see that it starts really low. It gets quite high as we get up to about 0.1 microns and up to 1 micron, and then it starts to drop again. So in the early part, there tends to be diffusion out. When you get to the larger particles, they tend to fall out. But then when you look at particle diameter and deposition, so that's how quickly they get removed from other, through diffusion or settling, you have high deposition, meaning high removal rate, until it drops, and then it starts going back up. And so one of the things that's really important is that like this 0.1 to 1 range, you don't have a lot of deposition and you do have a lot of penetration. So those are the ones that tend to stay in the air a lot more than the other ones. Because at these smaller levels, they don't get through as much and they diffuse out more quickly. So it makes it so like HEPA filters are targeting right around 0.3 microns, And that's because those are the ones that are kind of hardest to remove. And so if you do a really good job there, you can expect to get a you can expect to do a really good job of removing particles. Kind of at all the rest of the sizes as well. So a little bit about, indoor concentration of particles. And when we're talking about sapphires, what we're trying to do is try to get concentrations down. This equation doesn't have things like the technologies we're talking about, but the change in concentration with respect to time, there's the penetration factor, that's P. Gamma is the air change rate. So it's air change rate times outdoor concentration times the penetration factor. So how much is coming in and then what fraction of that. And then once it's indoors, you have air change rate because you've got air also going out, plus these other removal things such as deposition. Penetration factor is hard to measure. It's even harder to predict, but there are some good studies in the literature, which is what I'm really most wanted to bring forward in this presentation today. And so this is one of them. This was by Brent Stevens and Jeff Siegel, who I know Ellison knows quite well, Tammy. This is a paper they had in 2012. They measured in 18 homes, and these were down around the University of Texas. And what you'll see is that while there's some amount of scatter on average in these 18 homes, and these are submicron particles, on average, about half of the outdoor particles got inside. That's the penetration factor, on average, about almost half. Another thing that they did was they wanted to compare penetration factor with a bunch of different housing characteristics. So here are some housing characteristics, and there are statistics on Spearman's rank. And the ones in bold are significant to P of less than 0.01. The ones with the asterisks are P less than 0.001. Of interest to me is that these four here, C, ELA, ACH50, NL, those are all of those are metrics of air leakage of homes. So the things that really connect to penetration factors, how leaky are the homes. See, I'm not going to get into all of the different, what each of these is, but there's just not as much of a connection to floor area, volume, year built. It looks a little bit like year built, but year built is also pretty highly correlated with air leakage. So it really is about the air leakage of the home that tends to be really driving these things. Okay. This graph looks like a total mess. Oh, Tammy, you have your hand up.
Well, maybe you're going to get into this, but or maybe it's too complicated to address here. But how do people measure the penetration factor? They're not following little particles to see if they make it inside, so they must be measuring some ratio, and that assumes that the outdoors is staying constant for a while, so you measure how quickly it's getting in. Maybe that's too complex to get into here, but I'm just wondering if that's a thing you're going to address.
I was not going to address it. One of the absolute key things to do a penetration factor is to have zero indoor generation. If you have zero indoor generation, then with the equations, they can take this equation and calculate out P if you have no indoor generation. But it's hard to have no indoor generation if you have people in the house. So as always, the problem is the people. If we get rid of the people, none of these things are a problem anymore. Okay, so it looks like a total mess. I'm going to spend some time on this, but this is the graph, the single thing that I've seen in the literature that I've really wanted to bring forward the most. If you kind of look at trends instead of just mass, you kind of see that same thing, that 0.1 to 1. This is penetration factor on the Y. It kind of rises, you have more penetration closer to 1, where the particles are in that 0.1 to 1 range, and then it drops off again. But here's the thing, this paper from 2011 by Chen and Zhao, they looked at several different, or three different studies. One was Liu and Nazarov, one was Mosley et al., and then this one from Zhang et al. And the thing that's really fascinating to me about these is they were looking at, like, with the same size crack. So like here, we see 0.25 millimeter, 4.3 centimeter. That's the height and width of a crack. For the same size crack, they look at different pressure differences across that crack. That's what's happening with stack effect, with wind. It's creating these different sizes of pressure. And so I'm going to, just to have an example, I'm going to focus on the ones that are these solid black ones from Mosley et al. Because you can really pick those out, I think, more easily. So let's say we have a particle right around 2 to 2.5 microns, which is the upper end of the PM 2.5 range. The diamonds are where it's 2 pascals, and there's very little penetration. Now you get up to 5 pascals. That's the triangles. And all of a sudden your penetration factor is about 0.75. Then you get up to the squares at 10 pascals and the circles at 20 pascals. And pretty much all of the particles are getting pushed through. So the penetration factor has at some of these important size ranges, the penetration factor is really not just a function of how leaky the house is, not just a function of the crack size, but a function of the kind of driving forces we have. And so if we think about, say, middle of the winter, when it's not like it is now in 60 degrees, but how it usually is a lot colder, by having it colder, you have more infiltration because the stack pressures are larger, but you also are increasing the penetration factor as well. And so it's actually doing more than just bringing in more air. The fraction of particles within that air that are being brought in is going to be a good bit higher for some of these size ranges. When you get to these sizes where it doesn't matter as much, well, most of them are coming in anyway. But we do have at the lower end and at the higher end clear evidence that pressure really matters. And to me, that's a lot of why measuring these pressures is so important, because that's it. Part of why we're wanting to measure the pressures that Tammy and Dom are doing is so that we really can understand, so that we can be having our systems counteract those pressures. But it also has this importance in even how much stuff is coming in the first place. Tammy, your hand is up again.
I know, I'm sorry. I'll try to keep my questions infrequent and short. So when
We have plenty of time.
you're talking about the major effects on particles above 1 micron, when we're talking about smoke particles, they're going to sit right in the middle of this between 0.1 and 1 typically. So it's 300 nanometers or 0.3 microns is a good number to think of for smoke particles. I'm just wondering why there are so few measurements there and so many measurements at the ranges that are of less interest for smoke particles. And I know there's some, like, it's hard to measure specifically in that range. And I don't know if that's why that is, if it's just a measurement limitation, but it seems like we're really interested in this mid-range. I wonder why people weren't measuring there.
You're just seeing how much scatter there is over here and how little scatter there is over here.
Well, it also seems like there's a much larger number of measurements over toward 1 and 10, where typically very little of I don't know if it's a little bit of the particle mass, but it's certainly that's not where particles live. That's not where you see most atmospheric particles in that like 3 micron range. So why did they measure the ones that are less likely? And Christian, you're welcome to weigh in based on your knowledge of what you have seen in the data, ambient data as well.
Well, one of the things I want to point out is I think where, at each particle diameter measurement point, we kind of have most, if not all of these studies have data there. One of the things that's going on here is they're measuring, looks like, 1 and 1.1 and 1.2 and 1.3. So it looks like there are a lot more measurements because they're doing it at much finer gradations between particle sizes. But if you just look at how many symbols are there at any one point, I don't think it's actually all that different.
Okay, thanks. You may be right.
I was just gonna say, I wonder if maybe they were using particulate matter, especially if we're looking at PM 2.5 or something, maybe that being more important to be above the one. I don't know. I don't have an answer. I was just wondering maybe that could be one.
The other place that we've seen some of this is because a lot of this work was being driven by MERV. I'm not saying it's this one necessarily, but a lot of the people who have done this has been driven by MERV, and they don't do very well at those really small particles. Anyway, so they didn't measure at that much resolution because they all looked equally bad at the lower size ranges. So.
Yeah, and I certainly want to acknowledge what Tammy was saying, that if we're talking about smoke, it's these parts where there's not as much of an effect that are maybe most important. But one of the things about our technology is that it's not only for smoke. Whoops, I did not mean to go forward yet. And so when there are things going on that are more around over here or at some level down here, it does become, I think, more important, these effects. Okay, so that's really what I have found to be most directly talking about the penetration factor and what that really depends on. I do want to show a few other things that I think are of interest to us in general. This paper from 2000, they had, and I'm sorry, I'm just drawing a blank. I saw, I don't remember where these measurements were done. They have a lot of really fine details of particle size ranges. And at any size range, the two bars together will add up to 1, because it's what's the percentage that's indoor sources, what's the percentage that's outdoor sources. What we see is that kind of at the smaller range, outdoor sources tend to dominate, except like the 0.4 to 0.5s in these particular studies. And then as you get to larger, the indoor sources tend to dominate, suggesting that indoor sources often tend to be larger particles and outdoor sources tend to be more the smaller particles. But this is getting the indoor-outdoor ratio, not penetration factor. And so it really, we're not looking at how much of outdoors gets indoors. We're looking at the comparison of what is indoors versus what is indoors from outdoors. Another thing that I thought was very interesting from this is from a study near Leipzig, Germany, the particle diameter and the outdoor size distribution, urban with traffic, urban and rural. So it shows some of those things we've talked about how it's not just about smoke, it's about vehicles, things like that. So we see that a lot of, especially really small particles, when we've got a lot of traffic in an urban setting near Leipzig, Germany. The study, I believe, was in Los Angeles, done in papers from 2005, right near the I-405 freeway. So this is, again, looking at one of those non-wildfire, but much more common issues. And so the top graph, we've got, again, particle diameter, and then the number, particle, the kind of the number concentration. And we've got outdoor and indoor. This is from the daytime, 10 to 5, 10 a.m. to 5 p.m. And then they got nighttime, 10 p.m. to 6 a.m. One of the things I thought that was really interesting about this is that we definitely see these, that the outdoors has this higher, its peak is at, again, it's at a lower particle size than the indoor. And we see that in both of these, that they both do rise. I guess the peak at nighttime is similar. But then we're not having the indoor generation at night. So the indoors is going to look much more like what's coming from outdoors. But during the day, the peak for indoor is at a higher size. And then this is the indoor outdoor ratio. Of course, nighttime is less indoor, so the number is lower than in the daytime. But we also see this same kind of trend for the particle size for indoor outdoor ratio. That as you get to these larger sizes, the indoors tends to dominate. So again, if we're dealing with outdoors like we are mostly going to be looking at the smaller particles. This one I thought was interesting because, hey, with the work that MISA has been doing, I think we've concluded that MERV 13 isn't good enough. HEPA is what we need. This from Thatcher et al. In 2003, and these particles, and they put in a HEPA filter for a little bit and it drops like a stone. They remove the HEPA filter and starts going up again. So that's why we're doing what we're doing. It's just, we know we can get rid of these things if we put in the right kind of filter. Okay, that's everything I put together on particles to just provide some information about how particles move in from outside to inside, at what kind of rates and what it's based on. There are a couple things I thought might be interesting to people about gases. And this is a study that I did back, almost 20 years ago. For a moment there, I was afraid it was 30 years, almost 20 years ago. We were measuring combustion products indoors from people using unvented space heaters. At that point, we weren't doing as much in the way of PM 2.5. Certainly our group, we weren't measuring PM, so we don't have those numbers. But where you see this kind of dot shaded thing, that's when the unvented space heaters were on. And we see the carbon monoxide rising pretty strongly in each of those. What we also see is that we have these things unrelated to the fireplace. And so we thought that was interesting. We noticed that it was like right after 9 o'clock every morning, we start to see this rise. And what we learned after seeing this and mentioning it to the resident is that's right about the time he went out and started up his car in the garage every day so that he could go off and see his buddies for coffee. He was retired, and that was when he and his coffee club were getting together. So he'd go in, start his car, but then look, now we've dosed the garage, and it takes like most of the day for it to come back down. So again, this isn't directly from outside, but it is one of those things that can happen. Like if something is being generated in one of these spaces that's what we call a buffer space between the inside and outside, if something gets generated there, it can be there for a long period of time and gradually come in. And so we did a follow-on project. We were just looking at contaminant transport from garages. And so this is SF6 measurements. Inject SF6 into the garage, and it has this long decay. And then these are all the different spaces within the house. And so again, we see hours and hours and hours for, if we've got kind of an enclosed space that's got a dose of stuff, it'll take hours and hours and hours for that to get into the house, cause some amount of increase, and gradually come back down. So I know we got lots of time. Well, we got like 10 or 15 minutes. That's the last slide I have.
That's a really long decay in that house.
Yeah.
Like, did you have a estimate of an air change rate of the house?
We do. I'm thinking back to the houses that we tested, and they would have been probably in terms of natural in the range of 0.3 to 0.5 air changes per hour. But of course, this decay is the garage decay, not the house decay.
Yeah, I know, I was looking at the house and how it, so the garage is still feeding it, that's why it
Yep,
flattens out.
yep.
Mm.
I'm not sure exactly how this sort of thing factors into what we might be doing, but it is something that I found really interesting when we saw it 18 years ago or 17 years ago, whenever it was. Something we really didn't expect. And when we are talking about contaminant transport into homes, to the extent that these spaces can matter for anything that we're doing, I think these are things for us to acknowledge happen. So like I said, that's the last slide I've got. I'm figuring, I'm guessing some of you, none of this was at all a surprise, or you've already seen all of these things. Hopefully it was of interest to others. And if you have any questions that I can try to answer, or questions that I don't know the answer to, and I can get back to you about, like, where were these measurements done? Yeah. I can get it, I can try to get it for you.
I have initial reaction to this is that I really wish you had given this yesterday, because I just today submitted a proposal on resuspension emissions of electric vehicles on different roadway surfaces. And I never even thought about the decay component and how long it might take, especially in a garage and it contaminating the indoor of a house. So thanks for putting that thought in my head, and I think I'm going to utilize that in some future work.
It'll be the next proposal.
Yeah, there we go. Yeah, there's a lot of potentially interesting research in resuspension emissions of electric vehicles. So that's a direction I plan on going in some future work.
Hey, Paul, could you go back to the last one you showed us, the one with the pretty colors? Yeah, or there are a couple with pretty colors. Because I have a little problem with colors. Is the one that goes along the bottom, the one that humps up, it looks like a snake ate something. Which of those on your key is that? Is that the bedroom above?
This is the bedroom above.
And is that the bedroom above the garage?
Yes.
Okay, so then, and then when it says living room, I mean, I figure family room adjacent, living room distant, is that what the DIS means there?
Yes. Yeah, so that's these two that are kind of
Okay.
not all the way flat, but lower.
Yeah,
The green one that kind of starts a little bit higher and then it gets a little bit lower, that's the family room. That's just on the other side of the garage. And the
Okay.
living room kind of at the opposite end of the house. That's the blue one here.
oh, okay, thanks. I mean, I think this this was really neat to learn all of this stuff. And it's particularly interesting to see how it does act in the house. And then when you think about where the amount of time they stay in particular places in a house, that's kind of cool to think about and what that means for their exposure and stuff. So thanks. And like where you can kind of put the house together in your mind. So that's really cool.
Thanks.
Okay, but we want all our houses to be well mixed. So that, so that we can use tracer gases. Don't show me this. I was just thinking though, this is like totally wacky off the wall, but what about using a garage smoke bomb as a way to measure penetration factor? You'd have to assume that the cracks from the garage to the house were the same type as those from the house to outside. Yeah, I just thought you have a giant buffer space with some very likely cracks. And it would be more controlled than what was outside, but that's just a wacky idea.
I don't know. I mean, yeah, it may well be. I mean, certainly not all houses. It's not always going to be the same, because we don't tend to worry about having as many layers between the house and the garage. Like, you don't have to worry about water management on that wall, whereas you do for the exterior walls. So there are definitely going to be some differences. One of the things that this did is it actually required us to come up with some different ways to think about analysis. And because you can't just say the peaks at the same time, the ratio of it. So how do you do the analysis? And Zach Marin and our Illinois group came up with the idea that people really liked is what's the peak here versus the peak somewhere further in as his metric. So you're looking at peaks, but not at the same time.
Yeah,
Which
I think-
kind of maybe goes in the direction of a penetration factor.
yeah. Well, I think just so the rest of the group knows that in the Epic Homes, probably a thing that we didn't tell you is Paul's group and the weatherization community has ways of testing the leaks between the home and buffer spaces, and we've been doing those to the best of our ability at the Epic Homes. So if we encounter something like this, then we may have a little more information to apply to the analysis. And that would be like, we would test the leak between the garage and the house, because when you do a blower door test, you're really only testing inside the house to everything outside the house. So it's something that Dom and Will and Misa have become expert on.
A few more minutes if there's anything else. Seems like not, so I'll stop sharing because then I can see everybody. Oh, and Will's joined and Kari has joined. All kinds of people joined and I didn't even know they were here.
Well, thank you, Paul, for alerting us to all that science. And for those of you who are not used to thinking about particles, we do have to think about size. It's really easy to make a measurement and think you have measured particle mass. Sometimes that is true. Sometimes you have just measured something relating to particles being there. And the size of the particles in question can affect those measurements as well as affect how they behave. So those of you on the physical science side are going to be alerted to how particles behave and aerosol dynamics and all that stuff. And you're not excluded if you're not on the physical science side either. You're welcome to come and talk like, Erica, I didn't know you were doing resuspension.
It's a new direction, I think, inspired by you all and money opportunity.
I had one question about something Paul said, but it was somewhat offhand, so it might be picked up later. You mentioned some work that you're doing with MISA, differentiating between performance of MERV 13 and HEPA. Has that already been presented in this forum?
Oh,
I missed
I
it.
don't think so, Misa. I think the last time I presented on our results was before we got the HEPAs.
Yeah, since I've been here, I don't think so, that I can remember.
Yeah, so I think the answer is no, Ellison. But yeah, when we were really focused on testing MERV 13s and even accounting for the fact that we finally realized the dust track wasn't giving the right numbers, we still were only getting, we weren't getting enough of the particles. We weren't having a good enough particle removal with the MERV 13s to feel like that was really moving the needle very much. So we got a couple of HEPA filters and so the more recent tests that MISA has done using those has really shown that those are very effective. But we probably should be looking at an opportunity, maybe MISA, after you've done some more of the tests that we've talked about, where we're looking at different flow rates and different times and things like that. We should come back and present some of that. And we did just get a new dust track that should allow us to really do the tests better than we've been doing.
I'm gonna go down that vein even further. for the HEPA filters, do they have kind of the boxy shape that you've used for the MERV as well? Because the only time I've ever seen a HEPA filter was kind of in the like soda can sized cylinder. Is there, because that would really diminish your flow rates. Is there like another kind of HEPA that you guys would be using?
Yeah, you can go into the Airy Lab and see what we've got mounted right now. We have two different sizes of HEPA filters right now. Both of them are still 12-inch by 12-inch square. In terms of its cross section, we have 6-inch deep and 12-inch deep models. Now, these are not cheap, but they also have these metal housings. And I feel like the metal housing is going to make it a good bit more expensive. And for the sort of thing we're talking about here for the type of application we're talking about, I don't feel like you need to have the really heavy metal housing. And so MISA's been starting to communicate with the manufacturer that Christian put us in touch with or gave us information about to maybe look at some, custom HEPA filters that are still the 12-inch by 12 inches. I don't know that 12-inch by 12 inches is the right size. That's one of the things we could also vary, but it would also require bigger ducts. We're trying to make it so that the ducts are small enough to be able to fit in most houses. So that there's a balance here. But yeah, it is still that same cross section.
That's awesome. Yeah, I'm excited to see.
So John, just following up on something you said about the soda can, the term HEPA filter refers to its removal efficiency. And that type of filter or that high efficiency filter could be put in any kind of casing. So for instruments like the one that MISA is using for ethane, we put a HEPA filter on the inlet to keep particles out. That's a little thing like yay big. For some of John's work on pyrolysis, he's cleaning out the air with a HEPA filter about this big. And then for Paul's work in houses, the HEPA filters might be shaped like a furnace filter. So that term HEPA, it doesn't refer to its particular shape. It refers to its strength of removal.
I see. Yeah, that makes sense. The only time I had seen it before was in a lab with Shantanu. We were doing mask penetration efficiency. So we used a smaller one, but that makes sense.
Yeah, and everybody talks about the filter that they're using as like the only one there is, right? Like, oh, sorry, I think I was muted, but everyone talks about when Shantanu says a HEPA filter, he's probably referring to something about that big. And the only thing in common with what Paul is doing is the quality of removal.
I think the other thing for those who don't work with filters a lot, it's a minimum threshold. Right? There's wide ranges of performance because it's pretty coarse classification about how good things are. So there can be a very thin line between like a MERV 13 and a MERV 12 as an example, based on which side of the line it's on. So it could be quite a bit better than the rating that they have, and yeah.
And certainly
They're
as
not
it gets
all
dirtier.
the same. Right?
Yeah, certainly as it gets dirtier, the efficiency will increase. Until finally it gets to where it's so clogged no air can go. You've lost all the holes. But one of the things I looked at, I didn't look at it, Christian and I talked about it, is a little bit was the minimum efficiency for MERV 16 is not that much less than HEPA. But as Christian pointed out, nobody is saying they're making MERV 16s for the most part, because by the time you're going there, you're just getting HEPA. And so to get something that's specifically MERV 16 is likely more expensive than getting something that's called HEPA, because there's more of a market for HEPA. I believe that's what you were saying, Christian.
Yeah, nobody knows MERV 16, right? HEPA,
Yeah.
for right or wrong, if people know what it means or not, it's at least a term that somebody's familiar with. So I think they try to push to be over the line for just brand recognition. Nothing else. Consumer recognition, awareness.
Awesome. Well, thanks, Paul, for putting that together.
Yep.
And Sapphire's team join us over the next couple of years as we attempt to also infer penetration factors in very complex systems. Thanks, everyone. Have a really good weekend.
Thank you.
Tammy,
Take care.
do you have 2 minutes to look at some pressure, differential pressure data for anyone who cares
Yeah,
about these
I can see on
barometers? I
every-
just,
I'll stick
Yeah.
I
around too.
happened to finish
Okay.
it while we were doing. the
Okay, I'm gonna stop the recording, or do you want, I could
Yeah.
continue?
Doesn't matter.
Wants to see.
So we know who cares about manometers. Feel free to stay on. Let me just show you what we
Who cares
came
about
up with.
manometers? Everyone loves manometers.
Everybody loves manometers. Now I just need to figure out how to share my screen. So this is the latest data, and I can circulate this around. This is on a log scale,
Mhm.
5-ish minutes data points.
Okay,
Um,
SCP 810 is the thing you're using, Christian?
Yep, exactly.
Okay.
And then I couldn't come up with the name of what Paul's was while I was putting together this graph, so we'll update that. But pretty good. I think some of this noise here was just being able to actually keep a steady state
Mhm.
pressure, but looks reasonably promising. So this is down
Yeah,
in the range.
so what were you measuring? What was your reference or your source of pressure?
So we had a teed line on the pump, slowly changing the restriction on a sample line. So they're both the manometer, our new system, sampling from a common or polling attached to a common tap, changing the differential draw through a
Mhm.
tube. So we'll want to do this again, like in an outdoor piece and all that. We did that over the holidays and it did pretty well, but we just had so much variability with the wind going
Yeah.
on, it was hard to actually get any sort of statistics.
That's
Um,
okay. So what does it look like? What is do you have it with you or a picture that you can share? Just to get a sense of, I can come up too. Are you in your lab?
I don't know if I'll get this close enough without unplugging things. Nothing.
Okay, so,
We have to attach it to a logger and some things like that. That's the sensing piece.
yeah,
that
so
could
we
be
could just
on
run it. I've got 2 taps on the front and back of my house.
Yeah.
I mean, 2 taps on the front, 2 taps on the back.
Mhm.
So we could just run them side by side with a manometer.
Yeah, exactly. So I think the short takeaway for where we're at right now is it looks promising enough, I think, to put out to a home. I'm just gonna have Carson change it from 1 second logging to whatever you guys are using as your logging interval.
Is it 5 seconds, John? That we're using?
For the
Oh,
manometer itself,
Yeah.
it's 5. I don't know, do we want to just set it to? Yeah, we could set it to 5.
Yeah, let's just do 5. We often average it beyond that, but you can't unaverage things, so.
Yeah, okay. I'll have it keep polling at the 1 and we'll average to the 5, just so we're kind of on the same time step as you guys.
You have a data logger because our manometers log themselves, so we have not worried about creating a data logging platform.
Yeah, we'd send you the same thing. I just have it attached to a little board here on my
Okay.
desk, so we do the same thing for yours. So we'll just put it into a case and get it over to you. So we won't get it, it's not gonna be a today type of
Oh, no,
thing,
that's
but early
fine.
next week, we should be in good shape. We seem to lose most of our agreement. I can't figure out how to unzoom here. At upwards of like 30 pascals, which is I think way more than what you guys are caring about, but that's where
Yeah,
we
we're
started to
not-
see
We might have
deviation, and I
30
think that's
pascals
just turbulence through the meter, through the pressure sensor that we have. Because the one here, the way it works, it actually pulls a tiny fraction of air across an element due to that differential pressure. And so when it gets too high, it's too big of a flow, and we're getting too close to the upper range of the detector,
Sure.
and it gets
Okay.
noisy. But all looking promising is the long and short of it. So we'll get it
Yeah,
bundled up
it's
and
really
ready for
exciting.
you.
Okay, so
So-
Tom, I'm going to task you with that.
Yeah, sounds good. So just setting it up at your place alongside the manometers that are currently running.
Yeah, and I think probably what would be best is to make, like, I've got one going through the window, but I'll just make another hole. Holes are us.
Sounds good.
Yeah, so we can do a complete deployment here, like for this, for your house test, not a big deal, but if we ever wanna do it for, as part of this study, we'll probably get like $40, something like that. For a
That
complete
would be
setup.
helpful. That would be much helpful, since they're 1,500.
Alright, cool, sorry to keep you longer, just wanted to share that being, I had meant to be sending over the stuff for. quite a
That's
while
great.
here, so-
No, it's nothing to apologize for.
Yeah, thank you for showing it. Appreciate it.
Yeah, bro. That's all I got.
Thanks.
Bye.
Bye.